All right, we're live. All right, cool stuff. Data cleaning. So there's a running joke among data scientists that 80% of the time we spend preparing our data, and in the remaining 20% of the time we spend about complaining about the fact that we have to prepare data. And the reason why people have this complaint is because data cleaning is kind of the sad reality of the world that we live in. In data cleaning, what we're trying to do is transform our data so that we can actually use it for further analysis. Now, in an ideal world, our data will come to us in a very good format that we can just immediately read into a pandas data frame, and that we can immediately do like all necessary operations to like create a model and like draw some predictions or draw some conclusions from our data. But in reality, our data do not come to us in this format. We have to get our data to be in this format. Okay. So we often address structure, encoding or formatting of values, missing or corrupted values, unit conversion, and extracting features of complex values, such as getting the year from a timestamp. All right. Now, oftentimes you won't like sit down with your data and really like spend like hours and hours cleaning it before you do your analysis. In reality, what will often happen is you'll get your data and you'll explore it a little bit and you'll clean up some parts of it, but it'll look mostly good to you. But then later down the road, you'll like try to fit a model, and then you'll realize that your model just predicts 0 for everything, you know. And so then you'll look back and you'll think, okay, well, what happened? Do I need to clean my data some more? And you'll usually go back to your data after several iterations of like later stages of the data science lifecycle, and then find some more issues that you didn't realize were there before. So data cleaning is kind of like this iterative process where you explore your data, try to understand it, and then realize, there are issues here, I should go back and fix them, and then you explore your data once more. Okay. So all of these issues with data are very, very commonly seen in the real world. Zeros replace missing values. So the problem with zeros replacing missing values is, for example, if you're working with income data and you have some missing incomes, but you replace them with the 0, you're going to think that your average income of your data set is much, much lower than it probably should be. Okay? Spelling inconsistent. This happens all the time, especially with human entered data. I cannot tell you the amount of times I've had to email students who misspelled emails, like submitting really important Google forms. And in general, like humans just make mistakes when entering in data. When people enter in data, when you know that data comes in from humans, that should raise some yellow flags and tell you to be very cautious about what your data contain. Rows can be duplicated, rows can be missing, inconsistent date formats. So, you know, which of those dates here is September 10? It depends on who you ask, right? If you ask someone in America, they'll say the second one. If you ask someone in Europe, they'll say the first one. Okay, so oftentimes, like, these things just come up, and it's hard to know which one's the right answer unless you have some idea about where your data came from, like who collected your data. If it's not documented, then you may have to make some judgment calls yourself, or you may just have to forego using this data altogether because it's just too hard to use. Okay. I posted here a link to like a more comprehensive list of issues. I just posted the ones here that you will see very commonly. Okay. There is no worse way to screw up data than to let a single human type it in without validation. For example, I once acquired the complete dog licensing database for Cook County, Illinois. This database contained at least 250 spellings of Chihuahua. Even with the best tools available, data this messy can't be saved. They are effectively meaningless. Okay, so sometimes you just like can't do it. Or you can do it, but it will cost you like many, many hours of time, and you have to really decide whether it's worth your time. So this is just the reality of the world that we live in. Data collection is a messy process, and because it's a messy process, our data come to us in messy ways. Now we want to clean up our data so it's easier to use, and in this class we'll be focusing on getting our data into what we call a rectangular format. Okay, so a rectangular format is essentially what we've seen so far when we work with pandas data frames. We remember that when we work with pandas data frames, our data come to us in nicely formatted rows and columns. And that sort of format is especially easy and especially amenable for data analysis. Okay. In a data table, every column has values of the same type. So in a single column, we will not mix strings and numbers. we can use group and sort and join operations on these data. And there's actually like a very small branch of mathematics that deals with this, that deals with these relational data called relational algebra. So if you take a databases class, you'll almost certainly see some mention of relational algebra. And just keep in mind that it was designed to kind of like describe operations for data frames, and in fact has kind of inspired a lot of the data manipulation techniques that we use today. So the same underlying relational algebra underpins Pandas, it underpins the data science library that we use in Data 8. It also underpins SQL, which is a very commonly used data querying language. Okay, so relational algebra, when you learn it in a databases class, I think when I first learned relational algebra, I was like, what the heck is this, like sigma and like pi and all of this stuff? But you should just keep in mind that it's an abstraction over working with tabular data in general. Okay. Now, in contrast, we may also work with matrices from time to time, and we will certainly work with matrices later on in this class when we're working with statistical models. Okay, the difference between a matrix and a data frame is that in a matrix, all the values have the same type. They either all have to be strings, or they either all have to be numbers, or they all have to be something else. Okay, and in this class, most of the time we'll see matrices containing numbers, numeric values, and the difference here is that in a matrix, usually the columns are not labeled. Okay, in a matrix, we often use the Python data structure of a NumPy array, a two-dimensional NumPy array to represent numbers, as you've seen in homework 1. And so when you see a two-dimensional NumPy array, you should think matrix. And when you see a pandas data frame, you should think data table. Okay, we do not use grouping and sorting and joining on matrices. We instead use linear algebra, which is why we require linear algebra as a co-requisite to this class. Okay. Let's see. Talk about keys. So not all columns in a data table are created equal. Usually we'll have what we call a primary key of a table. The primary key of a table is the column or set of columns that uniquely describe every other row, every other column in the table. Okay? And what that means is essentially the primary key is like the identifier, the unique identifier for a row. I have here a few tables here, and you can ignore the foreign key up above. What we have here is something along the lines of customers on the bottom table. They make orders for certain products. So you can imagine a company like Amazon has tables that look something like the following, where they have a list of products, they have a list of users, and they record which users bought which products. Okay? And so for the customers table, you'll often see something that looks like something ID, in this case cust ID. And if these numbers uniquely identify every person in this table, then we say this column is a primary key. Similarly, if this prod ID column uniquely identifies every product in our database, then we say that that column is also a primary key for the products table. All right. Now, for the orders table, actually, okay, so there is a primary key for the orders table. And what you may notice is that the orders table also references other tables. Okay, so for example, if we're saying that Sam bought a water bottle on Amazon, then we want to record down that user Sam bought the product water bottle. And we do that we often see that done through what's called a join table, such as the orders table here, which records down the orders that people made. And what's interesting about the orders table is that it references other tables. The customer ID column in the orders table references the customer ID column in the customers table. Okay? When a column in one table references the primary key of another table, we call that the foreign key. Okay, so it serves as a reference to another row, and it's very convenient when we know what columns are the primary keys and what columns are the foreign keys, because they allow us to do data table joins. So we can join data together to create more complete or more thorough data sets. Okay, now let me ask you a question. I skipped this on the last slide by accident. Is the email address a good primary key? What do you think? All right, I see some blank stares. Why don't you talk about it with your neighbor for like 1 minute and then get back to me. Go. Okay. Someone told me my mic was off. I think my mic is back on. Are we alive? All right. So what do you think? Is an email address a good primary key? Yes? Anyone say no? Anyone say sometimes? Yes, all the way in the back. What's your name?
William.
William?
I think sometimes it depends on the domain in the email.
Okay, so William says it depends on whether you include the domain in the email. So for example, like sam@berkeley.edu and sam@gmail.com. Is that what you're referring to by domain? Okay, yeah, that's certainly valid. So I would say it depends, right? So if you're, let's see, if you're a company and your company has accounts for users and every account can only have one email address, and I think an email address would be a good primary key for a user of your product. But if you're a bank or something, I don't think an email address would be a good primary key because users can have multiple emails. Okay. So the answer to most things in data science is it depends. And in this case, it depends on what exactly you're doing and what you want to use it for. Yeah, name a question.
Hi, can you just explain like foreign keys one more time?
Yeah, sure. So your name is? Jennifer. So Jennifer asked, can we go over foreign keys one more time? And of course. So the foreign key is a column in a table that references the primary key of another table. So in this case, in the orders table, the orders table itself has a primary key, like 1, 2, in this case 1 and 2. But it also has a foreign key. And you'll see here that the foreign key is one, like the cust ID column here. And the cust ID column references the customer IDs in the customers table. And because the IDs from one table reference the IDs from another table, we call that the foreign key. Does that make sense? Do you have any further questions? Yes, question in the back.
So you're saying that the foreign key can be attached to another table that's completely separate in a subject matter?
Yes, that's right. And so the foreign key references other tables. It usually does not reference the same table. It usually references other tables, and in this case we say that it usually has to reference the primary key of another table. Okay. I'm going to talk now a bit about tidy data. So there's a particular type of data format, a rectangular data table that we actually really like to work with as data scientists, or at least try to like maneuver our data so that it comes to us in this format. Okay, they're called tidy data. The format is every variable in our data comes in its own column, every observation in the data comes in its own row, and every value in the table has its own cell. Okay, so it's a little bit more clear with a few examples. So let me give you an example of tidy data and untidy data. Okay. So I have here on the left a country, and let's say this table contains like cases of tuberculosis. All right, and we see here that in the first row we have Afghanistan in the year 1999 has 745 cases for a total population of 20 million. Okay, so in this case, every variable that we're interested in, the country, the year, the cases, and population, come in its own column. Every observation is the number of cases for each column in a given year, and that comes in its own row. And every value comes in its own cell, which means that we don't pair together like Afghanistan 1999 in one cell, we keep them in separate cells. Compare this with the table on the right-hand side here, which is not tidy, where we have Afghanistan 1999, but we have here cases and population as this column in this table here. Okay, so the idea behind tidy data is that every row is kind of like one observation of some outcome that you're interested in. Okay. One way to tell whether data are tidy or not is whether you can compare rows and whether rows reference the same thing. So in this case, for example, rows labeled 0 and 1 on the data frame on the right-hand side, you cannot directly compare them. They reference different things. One row says that Afghanistan has 745 cases of tuberculosis, and row number 1 says Afghanistan has a certain population of 20 million. Similarly, the table on the right here is also not tidy. So I have here the same tidy table on the left-hand side, and on the right I have an example of a table that's not tidy. This is something that you'll see quite often, where the years, or for example, like the values of some column are actually form like separate columns themselves. So in this case, we have here Afghanistan, and in 1999, we have 745 cases of tuberculosis, and in 2000, we have 2,666 cases. But those should become separate rows in a tidy table, because we're actually considering every observation here the country and year pair. Okay, so I think it'll be even more clear after a demo. I do have a demo for you guys. And I will show you now, let me import these guys. Okay. I will show you now a pretty realistic data set that you can find from the World Health Organization website. As I was mentioning before, this data set records down like attributes related to tuberculosis in different countries around the world in different years. Okay. Now we see here this big data frame. This data frame has 7,000 rows and 18 columns. We can't even display all the columns here. In reality, the original table has something like 100 columns. Okay, so that's not very rare to find. It's often the case that when you get data off the internet, it'll have tons and tons of columns, and you'll have to figure out how to work with these columns, what the columns mean, and which columns you're actually interested in versus which ones you're not. Okay. So in this case, I filtered out a few columns here, but I do want to show you the rest of the columns to give you a sense of what's going on. And you see here that there are a lot of columns, and the columns seem to be related. Some of the columns seem related to each other. Okay, so we have here like new rel M014, new rel M1524. So these columns seem somewhat related. These columns also seem somewhat related, but here's an F instead of an M. In this case, what I've done is I've taken a look at what we call the data dictionary. Okay, so when you're downloading a data set off the internet, what you should do is look for a data dictionary that describes what each column means, because data often come to you in like weird column names like this that have no meaning unless you have the data dictionary on hand. Okay, so in this case, I've looked at the data dictionary for us, and I found out that these new rel columns correspond to new cases or relapse cases of tuberculosis. This M or F here corresponds to the number of males or females. And this code right here, these set of 4 numbers, correspond to the age range. So in this case, 3544 corresponds to like males aged 35 through 44 years old. Okay, so this is all information that I found out by looking at the data dictionary. And what I want to do is I want to make this data tidy. Okay, pull up code here. Okay, Let's take a look. I think I've messed up my demo a little bit, but I still can show you what data look like. All right, so I have here TB. And what I want to do in order to make this data tidy is I want to take all of these new rel columns and make them their own row in my new table. Okay, so what I'd like to do is I'd like to say every row in my table corresponds to an observation for a country in a given year, for a given sex of a person, and for a given age range. Okay, so I want to split off all of these different new rel columns and make them and turn them into a single column in my table. Okay. I'll show you right now like the realistic workflow that I go through, or that I would go through if I were working with this data as like a data scientist in the world. So the first thing I notice here is that country ISO 2 and ISO 3 kind of all refer to the same thing. So they're kind of like different encodings of country. What I can do as a starting step is to drop the ISO 2 and ISO 3 columns. Okay, so I can write dot drop columns equals ISO 2, ISO 3. And now the ISO 2 and ISO 3 columns are dropped. I don't need them because they're redundant. When I know that I have to do a lot of data manipulation, what I'll do is I'll make use of something called piping in Pandas. Instead of writing my commands line by line like so, what I'll do is I'll create a function for every operation I want to do. So let's do drop. Let's define this function called drop ISO. And this function takes in a data frame and returns a data frame. So I will just replace this code with this. Okay. And now instead of writing this code, I can write tb.pipe drop ISO. I can pipe the data frame through the function. And Pandas will call this function with the data frame on the left. And the result will be a data frame that's returned from the pipe. So you see here that I've done the same thing in a few more lines of code. But the reason why I want to do this, the reason why I want to use piping is because I can pipe together multiple functions. So for example, if I define another function called square the year, I can say return df. I can do something like return df.assign year equals df year squared, or let's do times 2. And now I can pipe this function as well, like so. So you can see that by chaining together some pipes, I can essentially build up my data cleaning in a series of steps. And this final cell here is relatively readable given that I've named my functions in an informative way. Okay, so if I run this code now, the year column will be multiplied by 2. Okay. So I'm not going to do that because that doesn't have any meaning. I'm just trying to show you why I would use piping. Okay. The first thing I want to do is take all of these new rel columns and do what we call a melt operation. Okay. In Pandas, a melt operation takes these columns, all the new rel columns here, and kind of like manipulates them into a single column in my table. It'll be more clear when I show you, but melting is the primary way we turn what we call wide form data like this one into tidy data. Okay, so let's do, let's call this tidy up. And let me do pd.melt. Every row in my resulting tidy data frame will be identified by the country and year. And I think I can run this as is country. Do that. Okay. So if I run this as is, you'll see that now, instead of having a bunch of new rel columns, all my new rels are in my single column, which has like the uninformative column name variable, and the value here is NaN, and because the original value in the table for that column was NaN. So let me undo this step and then redo it so you can compare the before and after for this particular table. So before, I had a bunch of new rel columns. After, I'm going to have a single column with new rel as a value and the original count as the count column. Okay, so here we go. Before, and I'm going to run this now. After. Okay, so before and after. Okay. And so what's happened here is that we've done what is essentially the opposite of a pivot. Okay, so in a pivot, what we do is we take values and rotate them up to be the columns of a table. When we do a melt, the melt is pretty much the opposite of a pivot, where we take column names and rotate them back into the table so that their values in the original table. Okay. Now, I'm going to name these columns something more informative, and I can do that in the melt method itself. Okay. Now, I'm not going to explain every method that I'm going to use today. In reality, you won't have a list of pandas methods that you'll use, that you'll have on hand at all times. What you'll do is you'll do something like the following. You will go on Google and be like, pandas, how to unpivot table. Okay, then you'll go, pandas.melt method, or this first thing, or the second thing. Okay, and then I click here. I look at this documentation, and I look through the examples, and I realize that this operation is the operation that I want to do on my table. And then I go back to my notebook, and then I copy in this code, and I manipulate it a little bit until I get the result that I want. Okay, so what I'm showing you now is kind of an abbreviated version of this, but in reality, I do this search all the time. Okay. So I have here this table with new rel M014 and NAN, and what I want to do is split apart these columns so that I have one column for sex and one column for this age range. And I don't really care about this new rel thing anymore because all these columns here are new rels. Okay. So I can make another function called split entry. Something I like to do with these piping is I like to make a function that does nothing. Pipe my data frame through this function, and verify that nothing happens to my data frame. Now I can manipulate this data frame as I want to, and I can just rerun the two cells here to see the result of my data frame. Okay. Another reason why I use piping instead of writing the manipulations on individual cells is because the Python notebook or the Jupyter notebook hides the state of variables from you, the user. Let me explain what I mean. And I can almost guarantee you that this will happen to you in real life. So this is called the TB table. Let's say I'm trying to do something like drop the ISO2 and ISO3 columns. Okay. So if you're not using pipes, this is what you might do. You might do drop ISO2 and ISO3. And if you're smart, you may remember that most methods in pandas don't mutate the original table. They merely create a copy. So if I write TB here, the TB table will still have the columns ISO2 and ISO3. And so you'll be like, okay, I need to use in place equals true. Or you'll do something like TB equals TB.drop. Okay, one of those two options, either is fine. So let's say I do this. And this will work fine the first time I run the cell. But what will happen the second time I run the cell is that it will give me an error. Why did the error happen? Because I dropped two columns, right? And so it's not particularly nice that when you run a cell twice, the first time it works and the second time it errors. It's also not particularly nice that if I go down here and do some in-place operations on TB and then run some cells above, it'll error out. Okay, so in general, what I will do is to avoid having to think about, okay, how many times did I run this cell? Did I run it twice? Did I run it 3 times? If I ran it 3 times, the next time I run it, it'll be an error. Oftentimes that's just too much work to do when I'm trying to concentrate on data analysis. And so what I do instead is I do this piping thing. Okay, and when I do the piping thing, what I use is always methods that do not mutate the original data frame. And then at the very end, I will save this pipe into a new variable. Let's call it tidy. Okay, so that way I don't change the original data frame. I can rerun this piping cell as many times as I want. I don't have to worry about like rerunning my entire notebook every time I want to redo a change. Okay, so this is just like something that I personally do. You won't see this being taught. You won't see this being taught in a lot of classes, but it's just something that I found works for me. Okay, so I have to recreate this table now because I like screwed it up. Okay, so there it is, and rerun these cells right here. So I can, as you can see, I can rerun this cell as many times as I want. I won't get the error. Okay, cool. So let's split this entry column up. And to do that, I will write these lines of code, take the entry column, split it on the underscore, take the last element of the split. Okay, so if I do that, I will get out just M014, M014, F65, like so. And I'm going to write a lot of code here that you may not understand, but that's totally fine. Basically, this is just showing you the workflow that I use. So I would do first, I would want to take the first character of this series here as the sex. I want to take the remaining characters of the series here as the age code. Codes.stir. Okay, and then I want to drop the original entry column. So I want to drop like so. Okay. That errored out. Code is not defined. Codes. Okay. So essentially what I've done here, and the nice thing, okay, so the next nice thing that I do is the reason why I put every method call in a separate line is so I can say something like, okay, if I got an error in my last line, I can undo it and then rerun this cell. Okay, so if I want to go back and like show you before and after, I can do that too. So this is before, and watch the entry column. This is after. So I've separated out the M and the H code. Okay, and then I'll add another step. I think I won't show you this step. I'll just copy it from another notebook. I'll cheat here because this step is kind of tedious. But you can kind of understand what I'm doing here, which is I'm building up my data frame cleaning in a series of steps that I write in small functions, and then I pipe my data frame through each function one at a time. This helps me avoid issues of hidden state in a notebook, and it also helps me be more clear about what's going on. So you can't exactly read it, but you can almost read this code. You can say, okay, first I'm taking my original table, I'm dropping the ISO columns, I'm melting it, I'm splitting by entry, and then getting the age from the code, and I end up with something that looks like this. Yes, name a question.
Jesse, I have a question in function split entry. So the data frame dot assign is codes.str0. What will the output if I just write codes0?
Yeah, it's a great question, Jesse. So Jesse asks, I had to write codes.stir0. What happens if you don't put the stir here? Actually, I'll leave that as an exercise for you. So I'm not going to go through here and show you everything that I did. In reality, when I write this code, what I would do is something like this. I would write like one line here, return it, and see what happens. And then I would write like this line here, and so return it and see what happens. So I would build this up step by step. In the interest of time, I won't go through like the entire process, but then rest assured that when I actually wrote this code, I like did it very, very slowly and did it like step by step in order to get everything right. Okay. I'll give you a hint though. I'm pretty sure it errors out, although you can try it and test me. Okay. All right. And this right here is my tidy data frame. And the reason why we like tidy data frames is because not only are they easier to think about. So for example, before in my original table, I was not able to say in Afghanistan in 2000, how many males got tuberculosis? In my original table, I was also not able to say, do males get more cases of tuberculosis than females, right? So one way you can tell that you need tidy data is that you're trying to ask some questions about your data that require some grouping, but you don't have the columns you need to do the grouping, right? So for example, with this table, I can group by sex, I can group by age, I can group by year, I can group by country, and all those groupings make sense, okay? So tidy data is useful because it allows you to it essentially just gives you the flexibility to ask a bunch of questions of your data by doing grouping afterwards. The second reason why we like tidy data is because later on in this class, actually on Monday, we'll be talking about visualization. And in this class, we'll be using a plotting library called Seaborn. And Seaborn methods work really well on tidy data and not so great on data that's not tidy. Okay, so another reason why we use tidy data, I screwed up my demo. I screwed up my data here, so I can't show you the plots, but I can maybe ooh and awe you with the types of plots you can make with Seaborn in a few lines of code. So for example, actually I can show you in my original notebook. So for example, in one line of code, I can make a bar plot. The bar plot automatically has 95% confidence intervals on it. In one line of code, I can make a facet chart or a small multiples chart where I have here a scatter plot of the points. I have the line going through the points. And I even have the 95% confidence interval around that regression line, all done automatically for me by Seaborn. So this is the sort of thing you can do once you have tidy data and you're working with a library that uses tidy data. Useful stuff. OK. Go back to my slides here. All right. Let's talk quickly about data file formats. So in this class, you'll see us mostly use CSV files. CSV files, we use the pandas.readCSV method. And most of the time, you'll see us do something pretty simple that looks like pd.readCSV, tb.csv. But as you may know, there are a bajillion options for readCSV. And the reason why there are so many options is because basically what happens is someone tries to read in the CSV, they realize that there's a problem with the CSV file, and so they modified the pandas method to account for that problem. So you'll see here skipping the header, keeping the date column, parsing the CSV file properly, and you'll never read through all these options. Basically, what will happen is you'll try to read your CSV file, you'll realize that there's a problem, and then you'll think, oh, I should check the documentation to see whether there's some way I can just get around this problem. There's some built-in way to get around this problem. And then you'll thank heavens for the poor souls that had to hand code all of these weird edge cases into read CSV, so you, the data scientist, don't have to worry about, for example, whether you need to skip certain rows or not, or skip the footer of a CSV file. I didn't even know the CSV files had footers. Okay. All right. The one caveat that you should be aware of is very often, CSV files will not contain column headers. So what will happen is that you'll read in your data, but the headers of your data won't look correct. And oftentimes that happens because Pandas takes, by default, the first line of that CSV file as the labels for your columns. And sometimes your data do not come in that format. Sometimes you need to provide your own labels. So I just have here the gotcha and how to actually get around it. Okay. Other forms of data we call hierarchical data because they're not rectangular. Instead, we have what's kind of a parent-child relationship between the data or data to come in a dictionary format with keys and values. Okay. Some common formats are JSON, XML, HTML, and YAML. All four of those formats describe data that come in a dictionary. Okay, so instead of having rows and columns, they have a dictionary with keys and values. Okay. Basically, with these data, even though the innate structure is hierarchical, we can usually convert them to tabular data anyway and coerce them to be in that format. For example, for a tree data structure, we can have one column in a data frame be the node ID and one column be the parent ID. For a graph, we can have one data frame contain a table for the nodes and one table for the edges. So there are ways to kind of convert hierarchical or even graph structures into a data frame structure. And I'll show you one example of that right now using the YAML format. OK. So I have here some data about Congress members. And when I was a kid, I remember reading about Congress and reading about how Congress works and stuff. And I remember looking at these pictures of Congress members, and I thought to myself, man, everyone in Congress is so old. And then I grew up a little bit, and I still look at Congress members and I think, man, these fellows are really old. And so I wanted to know, like, are they actually getting older, or is it just me, you know? And so what I've done here is I've found the data for Congress members, and you'll see here that most of the data come in either YAML or JSON format. Some of them come in a CSV format. And to show you what a YAML file looks like, let's take this YAML file. And you'll see here that it's just like this long text file where it describes Congress members using a dictionary format. So in this case, ID is the key of the dictionary, and the value of the dictionary is another dictionary, and these are the keys and these are the values of that inner dictionary. I can show you what that looks like in Python. So this code here just downloads the file, which I already have. In general, in Python, if you have a file format that you haven't worked with, you don't want to write a parser yourself. What you want to do is you want to import or find a library that can read that file and just use that library, which is what I'm doing now. So I'm going to import the YAML module, which is built into Python, I believe, and then open up that YAML file, which I've downloaded from GitHub. We see here that there are 539 entries in this dictionary, legislators. I don't want to show you the whole dictionary because it's really big, but I will show you maybe the first element of it. So we see here, this Congress member's name is Sherrod Brown. We have here the data on Sherrod Brown, the birthday, the gender, the religion, Republican or Democrat, all of this stuff. So it's a lot of information, and this is now in a Python dictionary, not in a YAML file. All right, so I remember reading this in, and I thought to myself, 539, does that seem right? Does that seem right to you? Any ideas on what that number should be if we're looking at current members of Congress? Yes?
535.
There should be 535 if we're looking at like members of the House and members of, oh my gosh, I'm blanking on the names. But there should be 535. Why might there be a few more extra? Could count the vice president for the Senate, yeah. So we could look through this data, and in reality, if you're being serious about this, you would look through all this data and figure out where those extra 4 people are coming from. I believe in this case, there are like some observers to Congress, like from Puerto Rico, or people that don't have voting rights but still like sit in Congress anyway. In this case, we have a few extra people, but that's an example of where like your domain knowledge like comes into play and helps you like figure out what's going on with your data. Okay, let's get to my scripts here. All right, I have here the dictionary, and this dictionary is very nested. So I can take the ID key of this dictionary, I can take the Wikipedia of that inner dictionary, and I can get back Sherrod Brown by doing like some multi-level dictionary indexing, like so. Okay. For example, let's let X be legislators, the first one. So here's X. Here is the ID of X. Here is the name of this legislator. The bio, which contains some information about the person. And I see here that this birthday is is a string, okay? And I wanted to know how old this person is. And so what I can do is I can take that date, X bio birthday, and I can convert it to a Python datetime. So from datetime, import datetime. And what you would do is you have to like write a format string for this datetime, which I have already done. In this case, it is the year comes first, and then the month, and then the day. And so if I run toDate on this string here, I have back a Python datetime. And now I can do something that looks like, let's see here. I can create a new data frame, using that dictionary. So what I'm doing here is I'm just looping over all the values in that list I read from the YAML file, and I'm pulling out all the information for every single legislator. So now I have a pandas data frame, and I've constructed this data frame using the values from a dictionary or a hierarchical data structure. Okay. Now what I can do is look at their birthdays. So I can take, in Python, what I would do is datetime.now, and I can subtract this birthday right here. So let's do legdf.loc, and let's grab that birthday, like so. So I can see here that Sherrod Brown was born 24,000 days before today. But what I'm really interested in is the year. So let me pull up, scroll down here. I'll grab this line of code here, which essentially just adds a row to the legislator data frame where I take the year out of this data frame. Okay. So take the days, divide by 365, and I have here the age of these people. Okay. Now I can plot a histogram. I can see how old these people are. Pretty old, around 60. Okay. Let's see here, what do I have? I'm gonna skip this, take a 5-minute break, and let's fill out attendance. You're totally right. I need to open the form. Okay, resume collecting. All right, try now. Wait, okay, try now.
a question. Like, why the data frame you showed us is not tidy? It's untidy.
The original one. Oh, the one from the original data frame before I cleaned it.
Yeah.
The tuberculosis data frame.
Yeah, I think so.
Because basically, like one of the variables we're interested in is the gender or the sex, right? And in that data frame, for example, the sex is not its own column. The sex is like encoded in the columns, like in some other columns in like the column names of like a bunch of columns. But what it should be is it should be its own variable. It should be its own column in my table. Yeah. Another example is the age ranges are variables that I'm personally interested in, or like the variables, like oftentimes like tidy data kind of depends on like what you're trying to do, but most of the time, if you're noticing that the columns themselves encode some values that you're interested in, so for example, like male and female I'm interested in, and the age range I'm also interested in, those are much more easily manipulated if they're values in my table as opposed to labels of columns. And so basically if the column labels contain like data, then that data should be in the table and not in the column labels. Yeah. Hey. Oh, I see. You have to go. Your Wi-Fi had issues? I guess. Okay. Oh, that's fine. Just have them. Yeah. Just do that. Okay. Thanks. All right. How many of you guys still need more time to fill out the attendance form? I think I have a few more people. If you just raise your hands, let me know if you're still filling out attendance. Okay, well, one person just approached me, so I'm going to leave it open for a few more minutes. I'm going to move on now to missing values. Now, missing values happen quite frequently. As you saw in my first demo, that data frame was just packed full of missing values. And the problem with missing values is that you can't simply ignore them. So missing values may represent fields that were lost, fields that were hidden, fields that are supposed to be private, fields that like you may have collected your data and then lost some data, or the data may just have like been entered in badly and like not passed some validation check and have been removed. And the problem is, unless you know why your data are missing, you can't really ignore them unless you want to affect your analysis down the road. Okay. For example, some people don't have a permanent address. So if you have a database of people and you notice that some addresses are missing, it's hard to conclude whether the people in your database don't have a permanent address, like if they're living in their car or in a tent, or whether your database has just like not recorded data for some period of time. So it is certainly the case that in data in the real world, they change the data format over time. So for example, in that tuberculosis data that I showed you before, some columns have no values until 2013, and then in 2013 they had some new test on tuberculosis, and then they started filling in those values. So it's hard to know whether that's happening or whether something more interesting is happening with the data, unless you have some sense of where your data came from. Okay, so all this stuff is really important to know. And you can't just discard records, because discarding records results in a sample. So if your data come to you, as a census, but they have some missing values, and you decide to just drop the missing values, which is something that often actually happens, like if you're in a rush to get out some data analysis, then what you've done is you created a sample of your original data, and that sample is a non-random sample, oftentimes. That sample is usually biased. For example, people that don't report their incomes may be like really poor, or they may be really wealthy. They just might not want to report their incomes. And so dropping those values will bias your sample in various ways. Okay, okay, I have one more thing here. Another thing you can do with missing values that you'll see sometimes is what we call imputation, where we actually fill in those missing values with with replacement data or data that we infer based on other columns. You can do this if you're very principled about it and you record down every imputation that you do. But if you don't record down what you changed in your data, you're going to have a bad time because somewhere down the line, someone's going to ask you a question about like, oh, like, I wonder why our average here is much higher than it should be. And if you don't have a record of what you changed and why, then you won't be able to answer that question, and you may have to start all over from the beginning. Okay. Yeah, of course, the ideal way to deal with missing data is to go back to your data collection and try to go back to the source and find that data. So like you go find the person and ask that person like, did you mean to put in your address or did you like want to leave it blank? But in reality, that's not very practical most of the times. So oftentimes what we'll do is, the best we can do is we can either choose to ignore if it's appropriate. We can choose to impute values if that's appropriate as well, and if we have necessary statistical like ability to do so. Or we'll just call it a day and say this data is unusable because there's too many values that are missing, and I don't think you can trust the conclusions that I'm drawing from. Okay. One common imputation is replacing the missing values with the average. So for example, if you have a data frame of incomes and you have some missing incomes, one thing you could do is replace the missing incomes with the average income. Doing that, well, it's sort of reasonable in the sense that it won't affect your average income, but it will affect the variance of your income because you'll have a lot more incomes near the middle of your distribution as opposed to near the edges. That's just an example of how imputation is always an imperfect thing to do, and you should be careful to document what you do. Okay, to give you a sense of this, I'll go back to, I'm going to close this form. Any last words before I close this form? Closed. Okay, back to my data. Now, if I look at this legislator DF, actually if I look back at my legislators, I pointed out to you before that I had a bio attribute, and this bio attribute has a religion. Now, if I try to make this religion column a column in my data frame, so I have here my original legislator DF, which does not have a religion column. I can try to add that religion column to my data frame, so let me try to do that now. I can do that. One way I can do it is doing something like leg DF, religion, and I will get the bio, religion, for every legislator that I have. Okay, and when I do this, I will get an error. I get an error because some people don't have a religion recorded in this data. And so instead of using this bracket religion here, I need to use the get religion. The Python method get for dictionary says that if the value is not in that dictionary, then it'll be none. So if I do this, everything will be happy. And you notice that here I have none for these values, and I have Lutheran, Roman Catholic, and so for these values. Okay. And so if I say something like, gee, I only want to keep in my data set these good religious people, and I drop the people without religions from my data set. So let me do leg df. Religion is not null. This is a Boolean series which I can use to index my data frame. I have here only there are people that have religions, and I can plot this. Oops. Like so. Whoa, I need to get out the age column. And now people are really old. So you see here that when I take out people that don't have recorded religions, I skew my data upwards in terms of age. It looks like people who have religions recorded in this data are older. It turns out that in this case, one interesting thing about this data is that John De Niro used this demo last semester in spring 2019. And between spring 2019 and today, they removed this religion data because it was very incomplete. So when I actually downloaded this data and tried to run through it myself, I was getting all sorts of errors, and I couldn't figure out why. And so I did some sleuthing, which is something that you might have to do even later on if you're trying to recreate some of the demos in this class. You may notice that sometimes you get an error, and you'll have to dig back to the source to figure out why. In this case, I went back to this GitHub for this data set, and I found out that these people took out their religion field because it's very incomplete. They composed it from like the Pew surveys, but then they're like, let's not put it in, let's remove it. So what I actually did for today's demo is I've actually I went back to the last version of the data with the religion still intact and pulled it out. But if you want to actually run this, when we run this data on the current legislators for the United States, you won't be able to do this because no one has religion. Okay, let's talk about joins. Let's do that. Okay. Now I mentioned before that in data tables, we often have primary keys and sometimes we'll have foreign keys. When we have foreign keys, we can do what's called a table join, where we take two tables and join them together horizontally to get more information contained within each row. Okay? So in this case, pull up my slides here. I skipped a slide. I think there's a demo here. There is a demo. All right, let's go to my demo. All right, so in this case, Congress members are in committees. So as a member of Congress, you can join certain subcommittees of Congress where they discuss and vote on specialized bills, sometimes related to environmental things, sometimes related to taxes, for example. And so what I've done here is I'm going to download the data on committees. Okay. And I'm going to make a data frame out of these committees, out of the committee information. And we see here we have the House Committee on Agriculture, the House Committee on Appropriations, so on and so forth. We have 47 subcommittees in the House and Senate combined. Okay. If I look at, let's see here. I'm missing, oh, here it is. If I run this line of code, I also get back the mappings between committees and legislators. Okay, so what we see here is that each committee has an ID, each legislator also has an identifier, and this table here says the legislator with this identifier belongs to this committee. Legislator with ID N00181 belongs to the HLIG committee. This committee contains multiple people, so we see here all the committee members for this particular committee. But what I want to do is I want to say how old are the committees? So what's the average age of each committee, which requires me to know the ages of the legislators within each committee to take the average. Okay, so to do that, I need to do a join. And what I can do is use the pandas method merge. So if I have this member data frame, I can merge with the committee's data frame. And just for reference, I have the committee data frame here. What I want to do is I want to say, I want to match each row. I want to take this column of my committee's data frame and match it with this column here on the member's data frame. Okay, so you see here we have some matching IDs. The primary key of this table is the foreign key in this table. Okay, so that allows us to do the join, or do the merge in this case. So in pandas, this is what we call the left data frame, and this is what we call the right data frame. Okay? In pandas, we say, I want to take the left column ID. I want to take the column ID column of my left data frame and join it with the Thomas ID of my right data frame. Okay. So when I perform this merge, you'll see here that now I have one row for every legislator in my data set. And we see here that we see each committee appears multiple times, one time for each legislator. So this is also the same as doing a join in SQL, if you're familiar with SQL. And what I can do now is do one more join. So I will take, well, first of all, I can take these, I can save this table into a new data frame. Let's do that. Let me make this a little more readable. Okay, so now we can see all the code. Okay, like so. Now what I'll do is I want to take the member com data frame and join it with my original legislator data frame. So we see here that my legislator data frame has information on every legislator in Congress, And every legislator in Congress has an ID, the primary key of this table. In this case, the primary key of this table maps to the foreign key, legislator ID, in the member com table. So I can do another merge to join these tables together. All right, let's do it. Member com. And I'm going to merge it with the legislator DF. I want to take the leg ID column of my member com table. And I want to take, let's do right on. I want to take the ID column of my legislator data frame. Okay, so now I have every legislator I have in my data set, I've mapped them to every committee that they're in. So I have one row for every legislator committee pair. Okay, so every legislator can appear multiple times. Every committee can also appear multiple times. What I have here is the pairings of legislators to committees. Okay, now what I can do is say this, that. I have this data frame here. I can take the ages and I can group by the names of the committees, like so. And I can take the average age. So I have here now the average age of every committee. So let me zoom out a little bit here. There we go. And I can sort the values in ascending order. Okay, so now we see we have 47 committees, and we have here the average age of each committee. I was able to get this information by joining together three data frames. And if I had more foreign keys, I could just keep joining and keep merging until I get like some big old data frame that contains a bunch of data that I can use for further analysis. Okay, but here's something curious. Let me display to you. Let's see here. I hope this works. Rows equals 47. Okay. So I have here the expanded list of committees and ages. And we see here that the committees are really, really old. So we see here 55. But if you look at the average age of the committee member, let's take a look here. The average age of a committee member is 59 years old, but we have here only a few committees that are 59 years old, or have an average of 59 or younger, and we have a lot here that are way older. What might be happening here? Any guesses for why this could happen? Why we have many committees that seem way older than the average age of the committee member? All right, some more blank stares. Talk it over with the neighbor for 1 minute. Go ahead. Do some speculation. All right, any takers? Yes, name and proposition.
Colby. Maybe some of the committees with higher average age are smaller, and then the larger, then some of the younger committees, maybe they have more younger people, like that, or maybe as well.
Yeah, so Colby says maybe it's the case that these committees down here only have a few old people, and the committees down here are really popular and really big, so they have all the young people. Yeah, so that's certainly reasonable. Any other guesses? Yes, name and guess.
Yeah, Reagan, hidden pronouns. Just you have to serve longer to have a committee assignment. Usually, if you have to be older, you have to be in Senate or the House for X amount of years.
Yeah. So that's a great insight, Reagan. So Reagan says you have to serve a certain number of years in Congress before you can actually get into one of these committees in the first place. And I think that Reagan is actually right here. As you stay in Congress for longer, you join more committees. And so the older members of Congress have joined more committees, which makes those committees older. I can show you, or I can convince you why that's true, by looking at, let's see here. Let's take Seaborn. And what I can do is plot the, let's see here. So I have here data frame. What I want to do is take, let's see here, leg ID. Let's do that. Okay, so leg ID, value counts. Okay, so we see here that some committee members have joined 24 committees, whereas others have joined just one. And what I can do is convert this to a data frame so we can do some joining. Here we go. I have here the number of committees each legislator has joined. So I'm going to save this into a table. Do that. Okay. Now I can, let's rename these columns. Let's make that a little more readable here. Oops. That. All right. And then we will take this table and change the column names, ID and numcoms. All right. Now, I can take my legislator table and I can merge it with this table that I made here. So I can assign every congressperson the number of committees that person has joined. Okay, so let's do the merge. I want to join the ID column with the ID column of my other table. Okay, so I have here the each person along with the number of committees they joined, and I can now plot these on a scatter plot. So let's plot them. Let's save this in a data frame. And now I can use Seaborn to take a scatter plot or a regression plot of the age on the number of committees using my data frame. Okay, what do we see? We see a slight upward trend. So we see here that indeed, as you get older, it's more likely that you join more committees. This line here looks kind of flat. In order to tell whether there's actually a trend, we can do some inference. If you remember from data 8, we can bootstrap this regression line and see whether the slope could plausibly be 0. But I would say, looking at this plot and looking at our data so far, that it does seem to be the case that as you get older, you join more committees. All right. So to conclude, we have here joins. We can use pd.merge. One caveat is we say joining as the verb, and pandas has both the merge method and the join method. In general, you want to use the merge method. The join method behaves the same thing as a merge, but has some as a shorthand for merge. So there's some options that it hard codes in by default that you can't really undo. So in general, in this class, we'll use merge, but I'm going to use the verbs merge and join interchangeably because in real life, they'll be used interchangeably. Okay, reality is cruel. But now we know some techniques for addressing the cruel reality so we can do some interesting data analysis. Thanks for coming, and I'll see you on Monday.
It is merged also for them.